This is problem 1 from chapter 13. The 6-pound particle is subjected to the action of its weight and forces F1, which is 2I hat plus 6J hat minus 2K hat, F2, which is T squared I hat minus 4TJ hat minus 1K hat, and F3, which is minus 2TI hat. All three forces are in pounds, where T is in seconds. Determine the distance the ball is from the origin 2 seconds after being released from rest. So we're going to use Newton's second law, which says the sum of the forces is equal to the mass times the acceleration. So the first thing that we have to do is find the sum of the forces. Do not forget that it is subjected to the action of its weight in addition to force 1, force 2, and force 3. And the weight of the particle from the picture here would be acting in the minus k hat direction. So maybe we should just draw a new picture here. So we have force 1, force 2, and force 3, which they drew in the diagram here. However, well, force 3 is pointing in the right direction because that's the negative x direction. The other forces, it looks like the angle is going to change as time moves on. So initially, force 2 is just acting in the, well, 2I hat plus 6J hat, and there's no z component initially. That's for force 1. There we go. So that's in the xy plane initially. But there will be then a negative k hat component as time increases. And for force 2, they initially show it acting mostly in the y direction, but it looks like it's going to have a little negative k hat component also. So anyways, there we go. The important thing is to show force of gravity acting downwards. Okay, so that's all the forces are in units of pounds, so let's just leave the units off and say this is minus 6k hat, then add in all the other forces. Can we combine some things here? So I have 2I hat, I have T squared I hat, and minus 2I hat. So maybe I just want to do this all at once. So 2 plus T squared minus 2T is the I hat component for the net force. Then for J hat, I have 6 minus 4T, so this is plus 6 minus 4T in the J hat direction. And then for the Z component, I have 6 minus 2T minus 1 minus, whoops, that's not in the K direction, so 6 minus 2T minus 1. And then I think really all I can do to simplify this, because this is T squared, this is T, and that's just 2. This is T and this is just 6, so I can't add those together. So the only thing I can really do is subtract, whoops, this is supposed to be negative. So that would be a negative 7 minus 2T. And that's pretty much it. So that is the net force. Okay, then once I have the net force, I can do the net force is equal to the mass times the acceleration. So I just have to divide by the mass then in order to get the acceleration. So that's the net force divided by the mass. I wasn't given the mass. I was given the weight. But I know that the weight is equal to the mass times g. So if we're working with imperial units here, I would take the weight and divide it by g, which is 32.2 feet per second squared, in order to get the mass. Let's just stick that over here. So the mass is 6 pounds divided by 32.2 feet per second squared. 6 divided by 32.2 is 0.186, and a pound divided by feet per second squared is a slug. So I don't know if I mentioned that when we did the introduction to this chapter, but those would be the units of mass in FPS units. And while we're talking about the introduction to the chapter, make sure you read through sections 13.1 through 13.4 in detail. Okay, so now my acceleration is just going to be 1 divided by 0.186 times the net force. We can write it a little nicer. So that's 2 minus 2t plus t squared I hat plus 6 minus 4t j hat plus minus 7 minus 2 k hat. Okay, now we are looking for the distance from the origin when time is equal to 2 seconds. I have the acceleration, so I know that the acceleration is equal to dv dt. I can rearrange that and say dv is equal to a dt, and then integrate. The lower limit of integration is going to be 0, because time is equal to 0 to begin with, and the initial velocity is 0. And your upper limits of integration just keep as v and t. And then we know v is equal to ds dt. And when we rearrange that, we get ds is equal to v dt. And then once again, go from when time is equal to 0, and the particle is at the origin then, so s is equal to 0 also, and then you can just keep the upper limits symbolic, and then you will have s as a function of time, and then after you do that, you can put in 2 seconds. Okay, so you just have to integrate twice, integrate the acceleration with respect to time to find the velocity as a function of time, and then integrate that expression with respect to time to get the position as a function of time. And I don't really want to write out all the steps, but I'll tell you what you should get here. So for the velocity as a function of time, which you're going to get from doing the integration here, let's just leave the 1 over 0.186 outside, and then, we could do this. This isn't that hard. Okay, so integrating with respect to time here, I just think I'm going to run out of room though, so let's put it down here. Okay, so we integrate this. We get 2t minus, this is going to be, well, just t squared plus t cubed over 3 in the I hat direction plus 6t minus 4t squared divided by 2, so that's 2t squared in the j hat direction plus negative 7t minus t squared in the k hat direction. And this is the velocity as a function of time. Okay, and then we want to integrate this with respect to time to find the position. So the position with respect to time is 0.186, and then we have integrating this. This is just now t squared. This is minus t cubed divided by 3, and this is plus t to the 4th divided by 3 times 4, which is 12 in the I hat direction. And then we have 6t squared divided by 2, so that is 3t squared minus 2 times t cubed divided by 3, so 2/3 t cubed in the j hat direction, and this is minus 7t squared divided by 2 minus t cubed divided by 3 in the k hat direction. Okay, so we found s as a function of t, and now we just plug in 2 seconds for the time. Actually, you can plug in 2 seconds for the time and check to see that you get, when you simplify, 14.3 I hat plus 35.8 j hat minus 89.8 k hat. And this should have units of distance, which in this case would be feet. Okay, but they said to find the distance from the origin, so that would be the absolute value of this is a vector. This is a vector. That is a vector. So the magnitude of the vector would be 14.3 squared plus 35.8 squared plus 89.8 squared. That gives us 97.7 feet. So you can just fill in the missing piece here by plugging in 2 seconds for t and simplifying. And that is problem 1 from chapter 13.